aromatic amino acids. There are 3 of them that we have to worry about. The easiest one is, of course, just a benzene ring. Linked to the alpha carbon with a methylene group. Okay? This is called phenylalanine, PHE, and now we're in trouble because we already used the letter P for proline. So what are we going to use here? Well, we'll use the letter F for phenylalanine. Okay? I can make a molecule that looks almost the same. Except I can put a phenol ring on the end of it instead of an aromatic. And if I do that, the OH makes this a what? What's the other category I could have put this R group in? Yeah, it could be an alcohol, but I'm not. Its aromatic properties are more important most of the time, okay? And this is referred to as tyrosine. TYR. Now we're in trouble, aren't we? Because we used that T for threonine. So if we're going to use F for phenylalanine, we'll use a Y for tyrosine. Okay. Then I have one more here to show you. Let's space this out a little bit. Free electron pair sitting right there. Okay. And if I put this indole ring in here, right, you can see that here's my side chain. I have an indole ring. Okay. And this goes by the name tryptophan. Now we already used the T for threonine, so we're going to use the letter W because like Elmer Fudd, we're going to call this tryptophan, okay? So phenylalanine, tyrosine, tryptophan, okay? Now all of these aromatic residues have delocalized, they all have pi bonds, right? And so they all have delocalized electrons. And because they have pi bonds and delocalized electrons, this means that they will absorb UV light. And we can measure that absorption, of course, by taking, for example, a cube of solution of that amino acid, and I can apply a light with intensity I0, and I can measure the light that's transmitted. And of course, I, the transmitted light, will be less than I0 if this absorbs, as you well know. And this can be described with a famous law of physics known as Beer's law. Sadly, Beer's law has nothing to do with beer. Beer's law says that the absorbance, which is A, is equal to the logarithm of I0 over I, a number greater than 1 because I0 is greater than I. And this we'll define as being equal to epsilon times C times L. And I'm going to define those constants for you now. In that equation, epsilon is the extinction coefficient. C is the concentration of the solution, and L is the path length. Now in this course, or in any course, I will just remind you what you should naturally do anytime anybody gives you an equation, which is examine it in your mind and think, does it make sense? Well, let's see. It says that the higher the concentration, the greater the absorption. That makes sense. It says the longer the path length, the greater the absorption. That should also make some sense. And it says that there's this thing called the extinction coefficient. And what is that extinction coefficient? Well, that extinction coefficient, of course, is if I measure the absorption as a function of the wavelength, what I'm going to find is some maximum absorption, and the amount of absorption per molecule or mole of that gives me this fundamental property of the extinction coefficient. And if I measure this, for example, for tryptophan, what I get is a curve that looks like this. Let me grab some colored chalk. Curve that looks like this. I get an absorption here, and the maximum right here for blue for tryptophan, the extinction coefficient for tryptophan turns out to be maximal at 280 nanometers, and that number turns out to be 3,400 per molar centimeter. And that makes sense, right? Per molar centimeter, because I'm multiplying this times C and times L. Okay? If I do the exact same thing for tyrosine, I get a curve that looks like this. Okay? Tyrosine has a maximal extinction or maximal absorbance at 276 nanometers, and it's only 1,400 per molar per centimeter. Okay? Now, all of this is lambda in nanometers. Okay? Now, what's happening here? Well, you know what's happening. This is just a pi to pi star transition for either of those. Now, you may wonder, why is it that Professor Yaffe did not put on there anything about phenylalanine? And if you take a more advanced course, you'll learn that phenylalanine, in theory, has no absorption. It has very little, and that's because, as you'll learn in a higher chemistry course, that's a symmetry-forbidden transition, the pi to pi star in phenylalanine. So when we think about proteins, the two aromatic amino acids that do the absorption are tryptophan, single letter code W, I can't hear you, and tyrosine, single letter code Y. Okay. These are the guys that do the absorption.